In the last lecture, we were discussing solutions of the balance equations at steady state, but with internal sources or sinks within the flow. How do we solve these equations in this case? And I told you that if the source is a constant, right, if the system is at steady state and the source is a constant, right, then I can solve for the flux by just integrating the source. And then since the flux is related by the constitutive relation to the field variable, I have to integrate it once again. This integral can be done regardless of the form of the source, regardless of what the type of source is. This integration can always be done. If the source is a constant, then the integration simplifies, because the flux is just equal to the a linear function of position, and the field variable is a quadratic function of position. The field variable is a quadratic function of position, and the flux is a linear function of position. The slope of the flux is equal to the source density, the source per unit area per unit volume per unit time. So, the flux is equal to the slope of the flux is the source density. And I had illustrated that with the viscous heating in a channel. As you recall, in this case the velocity is linear. So, the velocity gradient, the slope of the velocity profile is a constant, and I had said that the source is equal to this function, mu times dvx by dz the whole square, which in this case is a constant because the velocity is linear and therefore the slope of the velocity is a constant. And we had solved the equation, we had solved the equation to get the temperature and the flux. We had solved the equation to get the temperature and the flux. As expected, the flux is a linear function of position. The flux is a linear function of position, and if you take the slope of that flux, the derivative of this flux, just take the derivative of this with respect to z, and you will see that it is exactly equal to the source here. It is exactly equal to the source here. So, the slope of the flux is equal to the source per unit volume per unit time. Integrate the flux once again to get the temperature profile. And in this case, the temperature is a quadratic function, parabolic. It increases, it is a maximum in the center and decreases to the wall temperature at the two walls. And we had calculated this maximum temperature as well. And from the flux we had got what was the Nusselt number, and that Nusselt number was related to the Brinkmann number in this case, where the flux is the average flux at the wall. Let us consider one more case where the source is a constant. And this particular case is the flow down an inclined plane. A flow down a plane inclined at an angle theta to the horizontal. We will assume that it is a steady state flow. Assume that the flow is at steady state. Thickness h. I will take the cross stream coordinate as z, streamwise coordinate as x. And it is flowing because of gravitational acceleration that is acting in this direction. It has two components, one is in the x direction, that is g sin theta, and the other is in the perpendicular to the flow, that is g cos theta. These are the components of the acceleration. The film is flowing in the x direction. The film is flowing in the x direction. The film is flowing in the x direction. Therefore, the velocity Vx at steady state is some function of the z coordinate. The velocity in the x direction is some function of the z coordinate. And we have to determine this velocity from the momentum balance equation. As you recall, the momentum balance equation is rho times partial Vx by partial t plus is equal to mu partial square Vx by partial z square plus the force density in the x direction, okay, mu times d square Vx by dz square plus the force density in the x direction. Okay. And at steady state this is equal to 0, this is equal to 0. Okay. And it is more convenient to write this in terms of the stress. Okay. We know that I can write this equivalently in terms of the stress as partial tau x z by partial x partial z plus f x. Okay. And here I have made the substitution that tau x z is equal to mu times d Vx by dz, a total derivative because Vx is now only a function of z. Fx is the force density, force per unit volume per unit time. Okay. Force is mass times acceleration, and therefore, force density is mass density times acceleration in the x direction, because we are writing a momentum conservation equation for the x direction, and therefore, this force is equal to rho g sin theta. G sin theta is the component of the acceleration in the x direction, that times rho is the force density in the x direction. Okay. What are the conditions at the two surfaces? Okay. At the bottom surface at z is equal to 0, the velocity, since the fluid is flowing over a stationary surface, the velocity has to decrease to 0 at that surface, okay, because the surface is stationary, and from the no slip condition the fluid velocity at the surface has to be equal to the velocity of the surface itself. Therefore, at this surface I have a condition that Vx is equal to 0. What about the top surface? Okay. At the top surface I have an interface between the liquid and air, or liquid and a gas. The viscosity of the gas is much smaller than the viscosity of the liquid, okay, in general. You recall that gases have a kinematic viscosity of 10 power minus 5 meter square per second, and the dynamic viscosity is of a similar magnitude, whereas liquids like water have 10 power minus 3. Okay. So, the liquids have 10 to 100 times, sorry, 100 to 1000 times larger viscosities than gases generally. Okay. So, if the viscosity of the liquid is much larger than the viscosity of the gas, at the interface you have to have a continuity of stress. Okay. You have to have mu liquid times d Vx in the liquid by dz. The stress in the liquid at the interface on the liquid side has got to be equal to the stress in the interface on the gas side. Okay. The stress at the interface on the liquid side and the stress at the interface on the gas side have to be equal. Were they not equal, you would have a finite force acting on an infinitesimal volume, and therefore, the acceleration will go to infinity. Okay. So, just the continuity of stress, the condition that the force cannot diverge implies that the stress on the liquid and the gas sides are equal. The viscosity of the liquid is much larger than the viscosity of the gas. Okay. So, if I divide throughout by the viscosity of the gas, viscosity of the liquid, okay, this ratio goes to 0. This ratio goes to 0, mu g by mu L tends to 0, and therefore, if the gradient in velocity on the gas side is finite, then the gradient in velocity on the liquid side has to be decreased to 0. Okay. So, the boundary condition that I have is that the velocity gradient has to be 0 when you have a 0 stress condition at the surface. 0 stress because you assume that the viscosity of the liquid and gas are equal, and for because the viscosity of the liquid is much larger, the velocity gradient has to go to 0, okay, at that interface, that is dVx by dz is equal to 0 at that surface. Okay. Therefore, I am solving this problem with the boundary conditions, okay, boundary conditions. Vx is equal to 0 at z is equal to 0, dVx by dz is equal to 0 at z is equal to h. Okay. So, those are the two conditions in this case. dVx by dz is equal to 0 from Newton's law also implies that tau xz is equal to 0. Okay, that is, you have a 0 stress condition at the surface. Okay. You have a 0 stress condition at the top surface and the 0 velocity condition at the bottom surface. So, subject to these two conditions, I have to solve for the equation in order to determine the velocity profile, the flow rate, and ultimately we will want to determine what is the in this case the Froude number, because the flow is being driven by the gravitational acceleration. Okay. Okay. So, this is a first order differential equation for the stress. Okay, this is a first order differential equation for the stress. So, I can solve it quite easily to find out what is the stress. Okay. So, in this particular case, this just gives me that tau x z is equal to minus rho g sin theta into z plus some constant a. Okay. That constant a is determined from the condition that tau x z is equal to 0 at z is equal to h. Okay. The constant a is determined from this condition. Okay. Tau x z is equal to 0 at z is equal to h. And if I just substitute that, it is quite easy to see. You will get rho g sin theta into h minus z. Okay. A just turns out to be equal to rho g sin theta into h. Okay. So, this is the stress that is exerted on the fluid, okay. And if you can plot the stress, you will find that it is a linear function of position. Okay. At z is equal to h, the stress is equal to 0, okay, and it increases linearly. Okay, and at z is equal to 0, this is equal to rho g sin theta into h. Okay, so, this is the stress profile. Okay, a linear profile for the stress, the slope of which is equal to the velocity profile. Okay. And once I have a linear stress, I can then use Newton's law to determine what is the velocity. Okay. Okay. So, the stress is a linear profile if the diffusivity is a constant and the source is a constant. Okay. If the diffusivity is a constant, the source is a constant and the flow is at steady state, stress is a linear function, and therefore, the velocity will become a quadratic function. Okay. The stress is equal to mu dVx by dz, and this will give us Vx is equal to rho g sin theta into h minus z the whole square by 2, okay, with a negative sign, because when I integrate h minus z, I get minus h minus z whole square by 2, okay, plus a constant. Okay. This constant has to be determined from the condition that Vx is equal to 0 at z is equal to 0. Okay. The no slip condition, Vx is equal to 0 at z is equal to 0 is used to determine this constant. Okay. And therefore, this just at z is equal to 0, a just becomes equal to rho g sin theta into h square by 2 mu. So, therefore, I get Vx is equal to rho g sin theta by 2 mu into h square minus h minus z the whole square. Okay. That is the velocity profile. Okay, that is the velocity profile for the flow down an inclined plane. Quadratic, it has a component proportional to z square, a component proportional to z, and a constant. No slip condition at the bottom surface. At z is equal to 0, you can see that Vx is equal to 0. At the top surface, z is equal to h, dVx by dz will be equal to 0. Verify that that is satisfied just by taking the derivative of this. Okay. I can also express this in terms of a scaled distance from the surface as rho g sin theta, okay, into h square by 2 mu into 1 minus z by h the whole square. 1 minus z by h the whole square. Okay, so, that is the expression for the stress. Okay. So, from this you can find out, for example, what is the total the maximum velocity. Okay. V max is at the top surface, right, because it has a 0 slope, that is where it is a maximum. It starts from 0 at the bottom, increases, and it has 0 slope at the top. So, that is where it is a maximum. This is equal to Vx at z is equal to h, which is rho g sin theta h square by 2 mu. Okay, that is the maximum velocity. You can also find out the average velocity. Okay. V average, okay, is equal to 1 over h integral 0 to h dz times Vx. Okay. This is the average velocity, and you can do that by expanding this out. Okay. So, all these terms are all a constant. Okay. All these terms are all a constant. Okay. Okay. 1 over h integral 0 to h dz of h square minus h minus z the whole square. Okay. And this I can expand it out. Okay. H square minus h square. Okay, expanding out h minus z the whole square. Okay. And this will cancel out. Okay. And this is equal to rho g sin theta okay. And if I integrate 2hz, I will just get hz square. Okay. And if I integrate z square, I will get z cubed by 3 between 0 and h. Okay. Okay, at 0 it is 0, at z is equal to h, this just becomes 2 h cubed by 3. Okay. And if I, in the end, I will get this as rho g sin theta h square by 3 mu. Okay. Because this gives me a factor of 2 h cubed by 3, okay, if you work it out. Okay. So, this is the average velocity, okay, rho g sin theta into h square by 3 mu. Okay. So, therefore, the maximum velocity is 1.5 times, 3 by 2 times the average velocity in this particular case, okay, because the velocity profile is parabolic. Okay. So, there is a relation between the average velocity and the maximum velocity for this particular case. And finally, we can get an expression for the Froude number. Okay. V average by root of g h, okay, which is rho g sin theta h square by 3 mu root of g h. and this I can write it as a dimensionless group, the Archimedes number to the half power times sine theta by 3, okay, where this is defined as rho square g h cubed by mu square. Okay. And you can easily verify that this is a dimensionless group. Okay. So, for a film of thickness h, okay, if you know what is this dimensionless group, okay, sin theta times Archimedes number to the half power divided by 3 is the Froude number. That is the correlation for the average velocity, okay, for the flow down an inclined plane. Okay. So, this is the relation for the flow down an inclined plane, where the velocity is a quadratic function of the height because there is a constant source. Stress is a linear function, right. It is 0 at the top surface and it is positive at the bottom surface. The slope of the stress is equal to the force density rho g sin theta. Okay. And from that you can use Newton's law to get the velocity. And from that you get the maximum velocity, average velocity, etc., okay, and all of the properties. Yeah. So, this is a simple example of flow down an inclined plane, an example where the diffusion coefficient is a constant. Okay. The viscosity is a constant and the viscosity is given by Newton's law. Okay, for now, you can solve the same problem if you have a varying viscosity as well. Okay. You can solve this problem if you have a varying viscosity as well. Okay. So, when we did dimensional analysis, I had told you about a power law fluid. Okay. Tau xz is equal to k dvx by dz into the modulus power n minus 1. Okay. In this case, since the velocity is always positive and the slope is always positive, I can equivalently write this as k dvx by dz whole power n. Okay. Okay, because the velocity is always positive and the slope is always positive. What happens if you have this power law fluid flowing down an inclined plane? How does the velocity profile change in this case? Okay. How do the relations change in this case? Okay. Okay. The point to note is that the expression for the stress still remains the same. Okay. If you recall, I had said that d tau xz by dz plus rho g sin theta is equal to 0 was the expression for the stress. That expression for the stress still remains the same. Okay. And therefore, the solution for the stress is still equal to tau xz is equal to minus rho g rho g sin theta into h minus z. Okay. Recall that that was the expression that we had got for the stress earlier. Okay. And that expression is now not affected by the fact that the constitutive relation has changed. Okay. So, therefore, I am going to get the same result here for the stress, okay, in this case as well. The relation between the stress and the velocity is now different. Okay. The relation between the stress and the velocity is now different, and because of that the velocity profile changes. Okay. In this particular case, k dvx by dz is equal to rho g sin theta into h minus z, and I have missed out an n power here. Okay. This is now different, and using this I have to calculate what is the velocity. Okay. Therefore, dvx by dz where k is referred to as the flow consistency index and n, as we recall, was referred to as the power law index. Okay. So, this has changed. Okay. Therefore, I have to integrate this expression, there is an h minus z as well, power 1 by n. Okay. I have to integrate this expression to find out what is the velocity profile. Okay. And recall that the integral of dz times z power alpha is equal to z power alpha plus 1 by alpha plus 1. Okay. Okay. So, that is the relationship between the height z and the index alpha. Okay. So, in this case this is 1 over n. Okay. Therefore, Vx is equal to rho g sin theta by k whole power 1 over n into integral dz of h minus z power 1 by n, okay, plus some constant. Okay. Okay. Integral of this is equal to minus of h minus z power n plus 1 by n. Okay. Alpha is now 1 by n. So, alpha plus 1 is n plus 1 by n, and I have 1 over alpha plus 1. So, I have to multiply that by n by n plus 1, okay, plus a constant. Okay. So, that is the expression for the velocity. Condition: velocity is equal to 0 at z is equal to 0. Okay. The boundary condition is that Vx is equal to 0 at z is equal to 0. Okay. Using that, I can easily find out what is the constant c. Okay. And the expression for the velocity is rho g sin theta by k whole power 1 by n into n by n plus 1, okay, into h power n plus 1 by n minus h minus z whole power n plus 1 by n. So, that is the expression for the velocity in this case. Okay. When n was equal to 1, that was when we had a Newtonian fluid with n is equal to 1, you got h square minus h minus z the whole square. This is the extension. Okay. And now we can calculate the maximum velocity and the average velocity. Okay. V max is equal to V z at z is equal to h. Okay. So, this is going to be equal to rho g sin theta by k power 1 by n into n by n plus 1 into h power n plus 1 by n. Okay. So, is equal to rho g sin theta h power n plus 1 by k whole power 1 by n plus, sorry, not plus, multiplied by n by n plus 1. Okay. So, that is the maximum velocity. Okay. We can also calculate the average velocity from this expression. Okay. V average is equal to these are constants, 1 over h integral 0 to h dz h power n plus 1 by n minus h minus z power n plus 1 by n. Okay. The integral from 0 to z divided by z is the average velocity. Okay. Let us evaluate that. The first term is h power n plus 1 by n times z, okay, because h is a constant. Okay. The second term, I integrate this once, h bar n plus 1 by n. Integral of h bar n plus 1 by n is alpha is n plus 1 by n. Alpha plus 1 will be 2n plus 1 by n. Okay. If you recall in our formula, alpha is equal to n plus 1 by n, therefore, alpha is equal to, alpha plus 1 is equal to 2n plus 1 by n. Okay. And you get a negative sign when I do the integral, and I will get h minus z for 2n plus 1 by n, okay, into n by 2n plus 1 between the limits 0 and h. Okay. Okay. At z is equal to h, right, the second term here, at z is equal to h, the second term becomes 0. You have only the first term, and that first term is equal to h bar 2n plus 1 by n. Okay. And at z is equal to 0, the first term is 0. The second term is, okay, h bar 2n plus 1 by n into n by 2n plus 1. Okay. And you take the value of z is equal to h minus the value at z is equal to 0. I can take this factor of 2n plus 1 h bar 2n plus 1 by n as a common factor, divide by h, I will get h bar n plus 1 by n, okay, into 1 minus n by 2n plus 1. Okay. And just a little bit of more algebra, there is a 1 over n here. Two n plus 1 by n minus n. So, I get n plus 1 by 2n plus 1. Okay. So, this is the final expression rho g sin theta h bar n plus 1 by k whole power 1 over n into n by 2n plus 1. Okay. So, that is the final expression for the average velocity. And you can verify that for n is equal to 1, this reduces to what we had calculated for a Newtonian fluid. So, these simple ways in which we can calculate the velocity profile, even if the stress, if the body force is a constant, you know that the stress is a linear function. If the body force is a constant, you know that the stress is a linear function, and then you just use the constitutive relation in order to find out what is the velocity profile. Okay. There is a simple case where the diffusivity is not a constant. Okay. The Newton's law does not apply. There is a more complicated expression for the relation between the stress and the velocity gradient. That is more complicated. Okay. That is this one. Okay. But still, because the body force is a constant, the stress has to be linear. And once you know the form of the stress, you can go back and calculate what is the velocity, the flow rate, etc. Okay. So, okay, that is a simple extension to the case where the diffusion coefficient is not a constant. We will consider cases where the diffusion coefficients vary with position in the next lecture. Okay. I will continue with this in the next lecture. I will see you then.